Okay, so I'm going to talk today about bloom filters. Before I kick off, could I just come to survey my audience? How many people know what a bloom filter is?
Is it something to do with forests?
Okay.
I looked it up on Wikipedia last night.
Cool. Good. So you're probably in about the same position as me, which is that I had heard about bloom filters, heard the term being passed around, and every time I went to try and find out what a bloom filter was, I encountered this kind of thing. What I particularly love about this explanation here is that it promises so much, it teases. Although equation 2 is accurate, it's difficult to interpret. Excellent, so you're going to make it easier for me? No, I'm not going to make it easier for you at all. I'm going to just give you another equally difficult to interpret version of the same thing. And I never managed to get past the maths. However, I saw...
maths? Another language.
So at this point I have to point out that the credit for the talk that I'm about to give has to go largely to a guy called Adrian Collier. This is really just a rehash of his talk at QCon, where he explained how a bloom filter works, what a bloom filter is useful for, in more or less maths-free terms. And I'm going to try and compress his talk down a bit. If you want to know more of the background and have more links to equations and complicated things, I would heartily recommend going and finding his slides. They're available on the internet, and they in turn have a lot of links to other useful resources. So, what's the problem that we're trying to solve? We've got a very, very big set of objects, and we want to know whether or not a particular instance of an object exists in that set. So a really good example of this is Google Chrome has a feature where certain URLs are flagged as being malicious or suspected to be malicious. And if you try to visit one of those URLs, it will say, "Ooh, are you sure this site's probably not up to any kind of good? You might want to go somewhere else instead." That list of bad URLs is extremely large, hundreds of millions of them. And that makes it quite difficult to send down to the client. If you packed the whole list of malicious URLs into the distribution and sent it down, it'd add about 300 megs onto the size of the Chrome executable, which would be a bad thing. So the alternative is, well, maybe we could have the list as a service somewhere that you can call into and say, "I'm about to visit this URL, is it good or bad?" And Google could say, "It's bad, don't go there." But that means you've got to make an extra HTTP call for every single request that you make, and that's bad too. Bloom filters give us a way around that problem. But to understand how that works, we need to understand a little bit about how hash sets work, first of all. So, suppose that as a naive Google engineer, I chose to implement the malicious URLs as a hash set. So let's have a quick revision on how hash maps and hash sets work. We have a function. So we have a list of data here, some strings in this case, and we define a function called a hash function, which can take any piece of data, any object, and turn it into a number. That function doesn't have very many properties, but one that does have is that it's uniformly distributed. So if I take a random selection of words, a random selection of inputs, then I should get numbers out on the other side, which are randomly selected across the whole range of integers. It's no good if all of my hash codes are small values or large values or even numbers or odd numbers. They need to be randomly distributed, more or less. And so the way that a hash set or a hash map or any other hashing data structure works is it first of all creates a number of pointers, which are commonly termed buckets. So my hash implementation here has 10. That's a very, very small hash map. A normal hash map would have probably a few thousand buckets. And whenever you generate So whenever I want to put an object into my hash map, I first of all calculate its hash code. So this one has a hash code 12 blah 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 0, and then I decide which bucket it's going to go into according to what the value of that hash code is. Now there are many ways you could do that. The way that Java does it is effectively it does a modulo operation. So if I have 10 buckets, it would just take the last digit. If I had 100 buckets, it would take the last two digits. That gives it some protection against broken hash code methods, because even if you're using sequential low integers for your hash codes, they'll still hash fairly evenly across the buckets. So having worked out which bucket to put it in, I add a pointer to it. And then I go on to my next one. This one ends in a 7, so I'm going to put it in bucket number 7. I go on to my next one. This one also ends in number 7. So what I do with number 7 is I make a linked list. So now I've got the first one I added in, then the second one I added in, then I can add another one into number 7. So now I've got 3 items in there, and so I go on. So I've got 2 in this bucket, 1 in that bucket, none everywhere else. This works quite well, but it has a number of disadvantages. The first disadvantage is the size of this set is necessarily as big as all the objects, because you're actually storing a copy of all the objects. In addition, you're storing a bunch of pointers to construct the linked list, and you're storing the buckets. So you're using up quite a lot of data there. The second problem is that if you use too few buckets, then you can end up with quite long lists here. So traditionally, we think about the get operation on a hash map or a hash set as being constant time. So you can pile as many objects as you like into your hash map, and it will always take roughly the same amount of time to return an object, because you just look up its hash code and go grab it out of the bucket. If your hash map is heavily loaded, so if you haven't used enough buckets, then the time to do a get actually scales up linearly with the number of objects that you're putting in, which quickly becomes a bad thing. Java's hash map is quite clever about this. It will count the number of objects going into the map, and if it detects that the chains are getting too long in the buckets, it will swap it out for a bigger set of initial larger set of buckets, so that it can carry on scaling up. Obviously, if you used a very, very large set of buckets for all your maps, you end up with a large amount of wasted data, because each of these is a 32 or 64-bit pointer address. So, you know, if you just made every hash map hold 1,000,000 items, you're wasting 1,000,000 words worth of data on each time. So that's okay if I'm the Google Chrome engineer, but it falls into the problem of having to send all the data across. So I've got all my 350 megs worth of rubbish that's got to be downloaded every time I want to send anybody a new version of the browser. Bit of a pain on the desktop, completely untenable on mobile. So what else could we do? Nothing, apparently. Bit vectors. Right, okay. So let's think about a much, much simpler and less effective solution. Suppose that I kept my list of buckets, and I kept my hashing functions, but instead of storing a linked list of all the words that had to end in that number, I just set one bit as soon as I saw one word that ended with that number. So if these are the only 2 words I know about, then I can and I have a bit vector that looks like this. I can definitely say that either one or other of these exists in the map. In particular, I can say unequivocally that if number 7 wasn't set, then neither of these exist in the map. If it is set, then one or other of them may be in the map. Okay, not very good though. How could we make that a little bit better? Well, how about if we use smaller buckets? If instead of having if instead of having 10 buckets, we had 1,000,000 buckets, then there would be a much lower chance of getting a false positive, because the range of possible hash codes would be much greater. So that actually makes it somewhat more effective. but at the cost of quite a lot of additional space. However, there's a cleverer solution than that, which is that you can use more than one hash function, and you can set, for each hash value that you compute for a particular object, you can set each of the bits in the bit vector that represents that hash value. And you can test whether or not a particular object is in your set by asking whether or not all the bits that all the different hash functions would have set for that object are set in your bitmap. So here's an example where I've got two hashes. So I've computed two numbers to represent this string and two numbers to represent that string. And you can see that the first hash code in both cases ends up with a 7, and the 7 is set. But for the second hash code, I have one that generates a 2 and one that generates a 0. The 0 is not set in here, so this bit vector cannot contain this item. This cannot have been added in here. This one could have been added. It's also possible that one of the billion other words which has both a 7 and a 2 as the last digit could have been set. But we've immediately made it a lot less likely that we'll get false positive results out of this. That, in essence, is all a Bloom filter is. So, here's the maths. If we have a particular number, k, of hashing algorithms, so k different hash code methods for our object, we've got n objects and a hash map with m buckets, then the probability of getting a false positive out of the map is that. Let's ask the same question again. What does that actually mean? So, suppose I have a list with 100,000 members in it, 1 million bits in my hash map, in my bit vector rather, and 7 hashing functions. That gives me a 1% error rate. So that lets me take 100,000 objects, put them into the map. I'm guaranteed to be completely accurate in my negative result. So if I ask the map, do you contain this string, and it says no, there is no error on that. It does not contain the string. If I say yes, then there is a 99% chance that that particular string was added into the map. So yeah, and you can see that if the objects we were talking about were URLs, then we would have saved ourselves a factor of 40. So that's pretty good. If we're prepared to deal with a small amount of inaccuracy, then we can make a huge saving in the amount of space. So we're quite used to thinking about algorithms in terms of a trade-off of space against time, or space against complexity. What this is really doing is adding a third point and turning that spectrum into a triangle and saying, well, you can trade off any of space, complexity and accuracy and choose whereabouts you want to be within that. So, back to our example of the Chrome malicious URL database. With 10 million URLs averaging 35 characters, that's a 35 meg hash set. Actually, it's a bit bigger than that, but more or less. Using a Bloom filter with 99% accuracy gets that down to 11 meg, which is pretty cool. That's quite a significant reduction. And so the way that Chrome works is it ships that Bloom filter with the browser, and if you request a URL, it will go and look it up in the Bloom filter. If the Bloom filter says, no, never heard of it, then that means great, your site is guaranteed good, you may go and browse at will. If the Bloom filter says, whoa, that looks a bit fishy, then Chrome will go and make a request back to Google's own malicious URL service and say, I think my user is about to go to a malicious URL, could you just check it for me? And the malicious URL service, 1% of the time, will come back and say, no, that's fine, off you go. But most of the time it will come back and say, yes, you shouldn't go there. So you can see now why it's called a filter, because the primary use case for these data structures is to sit in front of some expensive operation, a call across the network or a fetch of some data off disk or something like that, and avoid unnecessary invocations of that operation. So, hash functions. Where are we going to get our 7 different hash functions, or however many different hash functions we need? We need a set of hash functions. They need to be independent. So it's no good just taking your first hash code and adding 6 to it, or 12, or any other number. They need to distribute independently across the set of integers. The good news is that if there are a family of hash functions which are called 2 universal hash functions, and if you have any 2 of those hash functions, you can combine them together to make any arbitrary number of additional hash functions. So it doesn't matter how many hash functions you need for your particular Bloom filter. You can start with a pair of 2 universal hash functions and glue them together according to a complicated formula which you will find in Adrian's notes should you wish to peruse it, and it will generate for you as many different independent hash functions as you need. And the good news is that there are a number of implementations of 2 universal hash functions out there. Murmur hash, XX hash and SIP hash are popular ones at the moment. This is a useful point actually to talk about a security issue which may or may not be worth considering, and that's hash denial of service attacks. If I've got a hash set, it stores everything in a linked list, as we've seen, and it relies on the fact that if I put 100 items into a 1,000 bucket hash map, then on average 1 in every 10 buckets will have 1 item in. I won't get everything going into 1 bucket. If I know your hash function and I know how it processes input, I can tweak the input that I'm sending into your hash map so that everything lands in 1 bucket, which means that all of a sudden you've lost any hope of getting an O1 constant time get function. Every one of your gets is now traversing a long linked list. SIP hash is interesting because it explicitly protects against this kind of denial of service hashing attack. It uses entropy from the machine that it's running on to ensure that it distributes randomly across the integers and that you can't reverse engineer from it a way of designing input in such a way that it will always generate the same hash or always generate hashes that will hash into the same bucket. So if you're dealing with untrusted input, let's say for example you were hashing search terms which users had entered into a website, you might want to consider using something like SIP hash. If you're dealing with input where users don't have the ability to input it, I don't know, user codes say, something like that, where the system is allocating them out, then Murmur hash or XX hash are somewhat faster, have somewhat better distribution characteristics, and you probably want to use one of those instead. Yeah, so choose your hashes carefully. I don't know whether there have ever actually been any effective externally visible attacks using hash poisoning. It would be interesting to find out. Yes. I imagine there must be, because otherwise somebody wouldn't have gone to the effort of making a SIP hash. It's worth noting that these hashes are not cryptographic hashes. They're not designed to be cryptographically safe, they're designed to be fast. Hashing in Bloom filters is always the most expensive part of the operation, so you want a hash function which is as fast as it can possibly be, not a hash function which is completely bomb-proof. So you won't see things like SHA being used in Bloom filters, because it's too expensive. So where might you use something like this? Anything where you have an expensive lookup service sitting in front of a cache sitting in front of some kind of expensive lookup service, and you want to avoid calls into that. Database indexes, it's used all over the place. Oracle uses it to avoid having to go to the disk and fetch the B-tree index and go wandering through it. First of all, you look in a Bloom filter and say, well, if my primary key isn't in here at all, then I'm not even going to bother going to the disk, because you can keep the Bloom filter for a table in a tiny, tiny amount of memory in RAM, thereby avoiding ever having to hit the disks. Hadoop, Cassandra, all the big data databases do the same kind of thing, again, because you don't want to be pulling across several hundred megabytes of data, potentially over a network, in order to start hunting through it for a key that just doesn't exist. So for each of your H tables or whatever it is that Cassandra uses for storing its blobs of data in, you calculate a number of Bloom filters for the columns you want indexed, and then clients can cache all of those Bloom filters locally and just do a quick lookup in them before going off to the disk and saying, can I have all this data to go hunting through it, please? If you are in the genomics business, then this is really handy. You can take your enormous DNA sequence, which is broken down into individual genomes, and then you can ask it, does this genome contain this particular sequence, this kmer of combinations? It's used in smart routers that will detect network loops and things like that, again because you want to know, have I seen this packet before? Generate a hash from the packet, put it into a Bloom filter, gives you very, very fast lookups in a very small amount of memory, because of course routers don't have huge amounts of memory and huge amounts of CPU to waste on packet inspection. So it's used there. And I've just noted here that there is an Apache licensed Java client called Streamlib, which is used quite a lot, which gives you Bloom filters and a whole bunch of other probabilistic data structures alongside. So there's some other cool stuff you can do with a Bloom filter. You can use a Bloom filter to estimate how many things have been put into the filter, how many distinct things have been put into the filter, very, very cheaply. So if you imagine your Bloom filter, after you've put a certain number of items into it, some of the bits will be set and some of them won't be. So if you've got 7 hash functions, after you've put 1 item in, you will have exactly 7 bits set, guaranteed. After you've put 2 items in, you'll have some number between 7 and 14 bits set. If you're really unlucky, it might have hashed to exactly the same thing. If you're really lucky, it's probably hashed to something separately. The more bits you add in, the more likely you are to get overlaps. So the curve of number of bits set versus number of items added kind of goes up and gradually tails off. So you can pick where you are on that curve and get an estimate for how many items have been put into the set. Lets you do really fast counting of the number of items. There's an extension to Bloom filters called sketches, where instead of storing just a single bit field, if you've got 7 hashes, you store 7 bit fields, so you can see each bit that was set, and that then lets you count. You can draw histograms for the distribution of different terms, so you can see, or at least you can estimate, how many of the most popular terms are there. So the example that I've got here is a system that was processing logs, where each log entry would have a whole bunch of data, but embedded in that would be a 16-digit ID. And there are 3 billion of these things going through every day. So if you want to know, well, how many distinct IDs have we got, you can just use the cardinality estimate that we saw previously. But you can also ask questions like, what's the distribution? You know, do I have a small number of IDs that appear millions of times and then a large number that tails off? Or is it evenly distributed? Where are the quantiles? Those kinds of things. What you can't do is ask the Bloom filter to list the items that it contains, because that information is lost when you put the data in. You've thrown that away. I've noted at the bottom there is another data structure which is a kind of turbocharged Bloom filter called a hyperloglog, which is even more effective. It's specifically designed for doing this kind of cardinality stuff. So you can't ask a hyperlog, do you contain item X, but you can ask it things like, how many items do you contain, what's the largest number of items you contain, how many of the largest number are there, and how many of the smallest number. And it can do that in incredibly small amounts of space. So yeah, a hash set would have been, for this particular data set, would have been 120 gig, a Bloom filter was 12 meg, hyperlog log was 1.5 meg. And that's the kind of thing you can do. And I think that's about all I have. It is all I have, yes. Are there any questions? Did that make any sense?
Yeah.
I assume when you said after one entry you'd have exactly 7-bit set,
Yes.
you meant was you'd have between 1 and 7-bit set. If you're unlucky.
Yes, I suppose, yes, that's true. You could have had, you could have had all the hash functions hashed to the same bucket. Yeah, that would have been super unlucky.
Yeah.
But yes, you could have that.
Have you thought of any good applications for them in any of our projects yet?
There was something we were looking at the other day where we needed to look up very quickly, I can't remember what it was now, where we had a largish set of data that we didn't want to transfer all the way over from the server to the client. I can't think what it was, but I have seen bits and pieces where I've looked at it and thought, actually, this might be a useful technique. I think anything where you've got a cache, and in particular a cache where you expect the majority of calls on the cache to be negative. So, have you got one of these? No. Then having a Bloom filter sit in front of that makes it really efficient. One of the nice features about Bloom filters is that you can easily add new items to them. One of the unpleasant features is you can't take an item out of the Bloom filter, but if you have a system where you are continually adding items of some kind into it, then it's very easy to have a Bloom filter tracking all of the items that exist in the system at this point in time, that you can just continually update very, very cheaply by just saying, oh, there's a new one, add it in. You can also take two Bloom filters and merge them trivially by just ORing all the bits together.
Do you know if they're used by the Java caches like EH-cache?
I don't know. It would make sense if they were.
Did you mention 3D graphics as well at some point? That was misread.
I didn't. No, I didn't. No. I mentioned sketches, which are not anything to do with graphics, although they sound like it.
I wasn't referring to the
Yeah.
I was referring to some other day we're talking about.
Right.
I'm sure we need one.
Yeah. We're already using them. We're using them in Oracle. We just don't know about it.
It must not nice to write one, wouldn't it?
Where's the name come from? Mr. Bloom?
Yeah, Mr. Bloom. I can't remember what his first name is.
Orlando.
It could be, but I think rather unlikely.
Where they get Yorks.
Yes. Cool. I'm done.
Thank you very much.
Thank you.